Most coding agents can run one experiment, then they forget everything. Start another agent tomorrow, and it has no idea what was tested, what failed, or what it should try next. I built the missing layer, a loop where each fresh agent inherits the research, chooses one new hypothesis, runs the test, validates it, and leaves better evidence for the next agent. The goal is not one impressive result. It is a process that becomes more useful every time a disposable agent finishes. I will show you the framework, the 4 files that hold its memory, and 2 fresh agents actually using it. And by the end of this video, every strategy those agents ran is sitting in one dashboard like this, ranked, compared, and open for inspection. This is what we are building. A fresh coding agent reads 3 pieces of shared memory: the research mandate, my latest feedback, and the experiment journal. It proposes exactly one untested idea, runs it through the same backtester and validation checks, then appends the result before it exits. The next agent starts with a clean context window, but inherits the repository. The model is disposable. The research memory is not. Before any of the code, here is the finished system. Every completed run appears in one interface. I can rank candidates, compare their result curves, and open the full evidence behind an individual experiment. Nothing disappears because a new agent starts. Now let me show you how it is built. I did not build another backtester. I used Vibe Trading, the open source finance agent from my full Vibe Trading walkthrough. Give it a config and a signal engine, and it downloads the bars, simulates trades, applies costs, and writes the artifacts. That video is linked above if you want the full library tour. Vibe Trading already produces one strategy in one folder. What it did not provide was memory between folders. The design comes from Karpathy's AutoResearch. His version gives an agent a small language model training setup and lets it experiment autonomously. One file is editable, the evaluation code is fixed, every attempt gets the same 5-minute budget, and one validation metric decides whether a change is kept or discarded. The agent records the result and immediately tries again. The clever part is not a complicated agent framework. It is making experiments cheap, comparable, and persistent enough that the next decision can use the previous ones. I borrowed that research shape, not the machine learning code. The fixed evaluation harness becomes Vibe Trading. The editable training file becomes one new signal engine. Validation loss becomes a bundle of return, drawdown, sharp, trades, Monte Carlo, and walk-forward results, because markets cannot be reduced honestly to one score. And instead of keeping only the latest winner, I preserve every run. A failed hypothesis can be useful evidence for the next agent, so the memory contains losses and crashes too. The harness adds 4 Markdown files. Mandate defines the objective and constraints. Feedback is the human steering surface. Journal is the append-only experiment memory. And prompt tells every fresh coding agent how to use the other 3. There is no database and no orchestration framework. The repository is the state. Each invocation reads those files, extracts the tested fingerprints and gaps in the search, and states one hypothesis before touching code. Then it creates a native Vibe Trading run directory with config.json and one signal engine, launches the backtest, validates the artifacts, writes a plain language journal entry, and exits. Loop.sh starts another agent with a clean context, and the cycle continues with more evidence. The rules live in mandate.markdown, not in my memory. Every scored run uses at least 2 full years of Bitcoin data. Fees, slippage, and funding are explicit. Monte Carlo and walk-forward checks are required. Duplicate parameter fingerprints are rejected. And if the search keeps tuning one family, feedback can force the next agent into a different mechanism. Those constraints survive when the context window does not. A signal is not yet a result. The runner shifts it by 1 bar, so it cannot trade on a close it has only just observed, then executes at the next open. Entry pays the taker fee in these experiments, exits use the maker fee. Every fill gets adverse slippage, and an open long pays the configured funding assumption. The agent can invent the rule. It cannot invent a friendlier exchange. The harness is finished, so it needs a target. I chose Bitcoin momentum. Momentum is the deliberately simple idea that price direction can persist. In time series momentum, an asset is compared with its own history. A rule might stay long while Bitcoin is above a moving average, has a positive return over the last few months, or breaks its previous high. When the trend breaks, it moves to cash. This is different from predicting tomorrow's exact price. It asks whether the current direction is still in force. Why might direction persist at all? Markets do not absorb every change instantly. Investors can underreact, enter gradually, copy one another, or be forced to rebalance after a move has already started. Those mechanisms can turn new information into a trend rather than one perfect jump. Time series momentum has been observed across equity indexes, currencies, commodities, and bonds over horizons from roughly 1 to 12 months. But it is not a law. Trends reverse, and momentum can lose sharply when a crowded move snaps back. Crypto makes a useful laboratory because it trades continuously, moves through large regimes, and gives us public price data without waiting for a market close. Those same properties make it hostile. Volatility is high, returns are fat-tailed, and a fast rule can turn every burst of noise into another fee, spread, and bad fill. Research on crypto momentum is mixed, so the loop is not asking whether momentum works in general. It asks which precise rule, over which period, survives which costs. I ran the loop twice. The first agent saw an empty journal and chose a slow 50 over 200 day moving average baseline. It created the strategy source, ran the test, preserved every artifact, and wrote the result into the journal. The second agent read that evidence and chose a different family, a 120-day Donchian breakout with a 60-day exit. A second run folder appeared beside the first. That is the behavior I wanted, not blindly nudging one parameter, but broadening the experiment. This is deliberately not a grid search. A grid would turn 50 days into 40, 60, and 70, and call every combination research. Here the agent must say what the next experiment should teach. It checks which momentum families are missing, whether recent runs are clustering, and what the previous result failed to answer. A parameter change is fine when it tests a reasoned question. Otherwise, it moves to another mechanism. The journal makes that choice inspectable. Every run leaves the same evidence package: equity, trades, drawdowns, 1,000 trade order simulations, a bootstrap interval for Sharp, and 5 walk-forward windows. The interface warns when completed, trades are scarce. Monte Carlo can expose path sensitivity. It cannot prove a lucky parameter. Choice is not overfit. That is why every run remains a research candidate, not a system ready for capital. Then the agent writes what happened in plain language: the exact fingerprint, data dates, cost assumptions, metrics, validation, comparison, decision, errors, and one useful next test all land in journal.markdown. Old experiment entries are append-only. Only the small current candidate and coverage summaries change. A future agent gets quick orientation without erasing the history that produced it. If a run crashes, that failure is recorded too, so another agent does not waste time walking into the same error. Feedback.markdown is where a human can redirect the search without rewriting its permanent rules. If agents start tuning daily breakouts repeatedly, I can write, "Stop tuning daily breakouts. Explore a different momentum family." The next fresh agent reads that before it chooses. I can also require slower signals, test whether funding drives the outcome, or request a volatility filter. Mandate holds rules that should not drift. Feedback holds what I have learned and where to explore next. As run folders accumulate, the Streamlit dashboard discovers them automatically. At the top, the leaderboard defaults to Sharp instead of headline return, while trade count and drawdown stay visible beside it. Below that, I can compare up to 5 equity curves. Then I can open one strategy and scroll through its drawdown against Bitcoin. A second tab holds the trade order Monte Carlo fan and the 5 walk-forward windows. A third holds the exact cost assumptions the run was scored under. And the last one lists every preserved artifact and every individual trade. The dashboard does not calculate a second version of the result. It is only a viewer over the evidence already stored inside each run. The loop itself is a small bash script. Choose Codex, Claude code, or OpenCode, then choose the number of iterations. Each process gets the shared prompt and the local environment, does exactly one experiment, documents it, and exits. Nothing is copied between chats. The next process reads the files and preserved runs directly from disk. If the search is going in the wrong direction, edit feedback.markdown before the next invocation. There is one important difference from optimizing a language model. A lower validation loss on a fixed dataset is a fairly direct objective. A backtest is a historical simulation of a changing market. Try enough strategies, and one will eventually look exceptional by luck. That is why this loop does not automatically declare the highest return a discovery. It records sample size, warns about tiny trade counts, checks different time windows, and keeps every assumption attached. Even with those safeguards, the output is a research candidate, not a trading system ready for capital. The result is a backtesting process that no longer forgets after every run. Clone it, rewrite the mandate for your own hypothesis, and let the journal compound instead of restarting the conversation. All the code for this experiment, the loop, prompts, dashboard, and both completed runs is linked in the description. Subscribe if you want more reproducible builds like this.